Good day, everyone. I am Jian or Ibanez, a student from PSES 2, Group 1. Today, I will be presenting my article entitled Identification of Critical and Tolerable Fish Habitat Requirements based on Pre- and Post-Typhoon Data. So, this presentation is under the guidance of our teacher, Ma'am Idilyn Nunez. The authors of this article are Hong Peng Chiu, Jian Ping Shen, and Pin Han Chen, researchers who specialize in environmental and aquatic studies. Their works focuses on understanding fish habitat requirements and how natural events like typhoons affect aquatic ecosystem. The agenda of this presentation is first the introduction, objectives, area of the study, methodology, results and discussion, conclusion, and lastly, identify whether it is a quantitative or qualitative, discrete or continuous, and what are the level of measurement used in the article. So let's start my presentation and allow me to say again the title of my article, which is the identification of critical and tolerable fish habitat requirements based on pre and post typhoon data. So the study aims to recognize or to find at which habitat conditions are essential for fish to survive and which they can tolerate by comparing conditions before and after the typhoon. So what do you mean by critical habitat requirements and tolerable habitat requirements? So critical habitat requirements are environmental conditions that essential for fish to survive, growth, and reproduction, while the tolerable habitat requirements are conditions that fish can survive temporarily but may cause stress and reduced in performance. Objectives. Objective number 1 is to examine how major typhoons alter fish assembly gauge and river microhabitat. This objectives is about studying how typhoons change both the type of fish living in a river and the small habitats they rely on. Objective number 2 is to identify critical and tolerable habitat requirements of dominant fish species at different life stages, with the goal of informing post-disaster river restoration and eco-sensitive engineering. The study wants us to understand how typhoons affect fish and their habitats, figure out the most important habitat need, and use this knowledge to help restore rivers and plan environmentally friendly engineering projects. The study area is located in the upper part of the Qian Stream, a major tributary of the Gulfing River, the largest river in southern Taiwan. Qian Stream originates from Yushan Mountain. As you can see in the image, it consists of 5 streams that converge to form the Gulfing River. So, generally, the study section is in a rural, natural channel with fewer human modification. 2 stations were chosen for this study. The first one is the Nenchon Bridge, and the second one is the Holy Mount Zion. This area experienced 2 strong typhoons, providing an opportunity to compare pre- and post-typhoon conditions. Methodology. It involved comparing pre- and post-typhoon using 2 sampling period datasets, November 2008 to 2009 and May 2011 to March 2012, from 2 stations in Qian Stream, Taiwan, following typhoons Morakot and Panapi. Fish were sampled using electrofishing, focusing on 3 dominant species, the Hemamizon formosanus, Rhinogobis nantinensis, and Onychostoma alticorpus. Habitat variables such as water depth, flow velocity, substrate composition, and water quality were measured, and statistical analysis were used to distinguish critical from tolerable habitat factors. The methodology involves comparing fish populations and habitat conditions before and after major typhoons, focusing on dominant species, measuring environmental variables, and using statistical analysis to determine which habitat features are critical or tolerable. So, the statistical analysis they used in this article were the independent sample t-test and Pearson's correlations. So, first, each environmental factor was analyzed using an independent sample t-test comparing the habitat use of fish species before and after typhoons. If this test detected a non-significant difference in fish habitat, then the factor was considered a critical habitat requirement. If it shows a significant difference, these environmental factors that combined fish abundance were analyzed using Pearson's colorations to determine tolerable habitat results and discussion. Figure 1 shows the physical habitat before and after typhoons at the Chen Bridge. Figure 2 shows the physical habitat before and after typhoons at Holy Mount Zion. The table shows that typhoon had different effects on the three species in terms of abundance, length, and weight. For Himamizan formosanus, there was a clear decline in abundance at both stations, dropping from 384 to 177 at Minshan Bridge, and from 389 to 151 at Holy Mount Zion. Its standard length and weight also decreased, indicating that not only were fewer individuals present after the typhoons, but the remains of fish were generally smaller and lighter. In Rhinogobus natinensis showed a slight increase in abundance at both sites, rising from 57 to 78 and from 71 to 75. However, despite this increase in number, its length and weight decreased, suggesting that the population after the typhoon consisted mostly of smaller or younger individuals. Onychostoma alticorpus experienced the most significant changes with a sharp decline in abundance from 140 to 23 at Mount Chen Bridge and from 102 to 6 at Holy Mount Zion. Its length and weight also dropped drastically, especially at Minshan Bridge, indicating that this species was highly affected by the typhoon. Overall, the data suggests that while some species may increase in number after disturbance, most experience reductions in size and weight, with Onocostoma alticorpus being the most vulnerable and Rhinogobus natinensis showing some level of resilience. The table presents the critical environmental conditions for selected fish species before and after typhoon events, highlighting changes in their habitat preferences. For adult Himazizon formosanus, water depth slightly increased from 33.16 cm to 35.03 cm, while pebble composition rose from 23.90% to 32.60%, indicating a shift towards slightly deeper waters with more coarse substrate after the typhoon. For adult Rhinogobius natinensis, water depth increased from 29.62 cm to 22.73 cm, while sand percentage increased from 1.50% to 7.70%, and pebble composition decreased from 46.90% to 32.30%. This suggests that the species moved to shallower areas with finer sediments following the disturbance. In contrast, juvenile Onychostoma alticorpus show a decrease in flow velocity from 0.57 to 0.48, along with a slight increase in the variability of flow from 0.22 to 0.25, indicating a preference for slower but more variable water conditions after the typhoon. Overall, the data shows the typhoons altered habitat characteristics such as depth, substrate, and flow, leading to adjustment in the environmental conditions occupied by each species. Discussion. Typhoons reduce fish abundance, size, weight, and transform river habitat from coarse, diverse substrate to finer and more uniform conditions. Critical habitat requirements differed among species and life stages. Although Thymoxizon formosanus depended on stable water depth and pebble substrate, while Rhenegobius lentiensis required constant water depth, sand, and pebbles. Onychostoma alticorpus relied on stable flow, velocity, and flow variability. And the conclusion. Major typhoons significantly alter river habitats and fish communities, maintaining species and life stages. Specific critical habitat conditions is essential for fish survival, and identifying these requirements is crucial for effective nature-based river restoration after extreme flood events. To help fish survive after such event, we must know exactly what habitat they need at each life stage. So, protecting and restoring this critical habitat is the key to a successful eco-friendly river recovery. Lastly, I will identify whether the study is quantitative or qualitative, whether the data are discrete or continuous, the independent and dependent variables, and the scale of measurement used in the article. Based on the analysis, the article is quantitative in nature because it involves numerical data such as measurements of fish abundance, length, and weight. These variables are primarily continuous as they take on a wide range of values and are measured precisely. The independent variables are the environmental and habitat factor that change due to typhoon. These include water depth, temperature, water quality, as well as the occurrence of typhoon. These variables are considered independent because they influence the ecological conditions of the river. On the other hand, the dependent variables are the biological responses of fish, particularly fish abundance, species composition, fish size, and habitat. These outcomes depend on changes in the environmental conditions caused by typhoon. In terms of scales of measurement, the study mainly uses the ratio scales since the data have a true zero point and allow for meaningful comparison. Interval scales also used in the article, such as water temperature, are measured or an interval because they have no true zero. Overall, the article relies on quantitative, continuous data measured at the ratio scale to support each findings. And that would be all for my presentation for the identification of critical and tolerable fish habitat requirements based on pre and post typhoon data.